Okay, well that's it. Welcome to Calculus. You should have completed Chapter P, which were the prerequisites to the actual calculus. So this chapter is on limits and their properties. So like before, you're to take notes while watching the video, answer the practice problems, and then if there are any questions that you may have, you should write them down. So Chapter 1, Limits and Their Properties. So 1.2, Evaluating Limits Graphically, Part A. This should be page 11 of your notes. And if you ever saw how the movie Mean Girls, she enters into a math contest in which one of the answers to the questions is the limit does not exist. Maybe you're like, what's that? Well, hopefully now you'll learn. So what is a limit? Here we have a function f of x equals x squared plus 3. I have the graph. And suppose we wanted to find the limit of f as x approaches 1. This is how it's said. And the way that it's written is right here. Okay, it looks weird, but it's the limit of the function f as the x value gets close to the number 1. And that's what that stands for. In calculus, there are several ways to do this. And you need to be able to do all of these. Um, you should be able to find limits graphically, which means actually looking at the graph and then telling me, oh, the limit as x approaches whatever number is this. Numerically is when you're actually going to set up a table. And the table, you're going to analyze the numbers and see what number they're approaching or getting close to, and then that'll be the limit. And then algebraically or analytically is just doing the algebra, doing the math, taking the equation and either plugging in the number to see what it equals or having to do other various steps. So to start off, evaluating graphically, there is such a thing as one-sided limits and two-sided limits. So we have the right-handed limit and the left-handed limit. The right-handed limit is the behavior of the function from the values greater than whatever given x. The left-handed limit is the behavior of the function from values less than the given x. Now, the notation for left and right-handed limits is slightly different than the notation that I described above. So we're going to call the x value, we're just going to call it a. From the right, the notation is going to have a little plus sign right after whatever number that is. So here it's a. And then for the left, it's going to have a little negative, a little minus. So plus is going to denote right, and minus is going to denote left. And if you'd like, you can think of a number line, right? Here's 0. All of these numbers are positive, and all of these numbers are negative. And that would be the idea behind that. Then we also have two-sided limits. And two-sided limits is the combination of the right-handed and the left-handed limits. I tend to call it the overall limit. Now that's not a proper vocabulary term. I just like calling it the overall because you're looking at both sides at the same time in order to figure out what the actual limit is. If the two-sided limits, if the two-sided limits, if each one-sided limit is the same, then the limit exists. And then the notation is, as mentioned before, there aren't any pluses or minuses. That's an indicator that it's both right and left-handed limits together, and then you're just finding the overall limit. Okay, so back to the very beginning. Let's actually discuss the limit of that function as x approaches 1. So here's a graph of x squared plus 3, the parabola. And if I'm trying to determine the limit as x approaches 1, of this function, then I'm going to look at where this graph is when x equals 1. So here is x equals 1. And at x equals 1, this graph is equal to 4. Now, this is a simple graph, so my limit can just be found by taking my 1 and plugging it in to the function. If I do that, right, 1 squared plus 3, that is 4. My limit happens to be 4. Now, the right-handed and the left-handed limits. If I approach from the right side, this is approaching from the right side, the closer I get to where x equals 1 is, I should be able to determine what the height of my function is. And it is 4. Now as I approach from the left, and here's the left side, same thing. I need to know where this graph is, and it's at x equals 4. So in this case, both my left and my right are both 4, therefore the limit exists, and the answer is just 4. Okay, this is the idea here. So we would answer this by saying the limit of f as x approaches 1 is 4. Now, hopefully you've noticed my notes are in Cornell style. So I'm going to, from time to time, give you questions that I believe are questions that you can use to study. If you've never used Cornell notes, the left column are questions that you would ask yourself, kind of like when you're using note cards or flashcards, and then you would cover the right side to see if you know the answer to that question on the left. So I'm going to write down a question that hopefully you can use to study. So there's a question, what are different ways to find the limit of a function? And then hopefully with the right side covered, you'd be like, okay, that's graphically, numerically, and algebraically. Now, I'm not always going to write the questions. Sometimes I'll indicate verbally, this is a good question to have on the left column of your page. Alright, so example 1, use the graph to find the limit if it exists. If the limit does not exist, explain why. So for A, I have a function here. It's a straight line, but I do observe a hole. Right? Hi, little hole. I see you, my friend. And so the limit as x approaches 2. So 2 is right here. Oops. So my height at x equals 2 happens to be y equals 2. Now, from the left, let's see. From the left, I end up at 2. Oops. From the right, I end up at 2. Therefore, the limit is 2. This is supposed to be, or rather, this is a simple question. I do realize that there's a hole. And for limits, it really doesn't matter whether or not the function exists at the value you're trying to approach. The question is, what value does it seem to be getting close to? And it gets close to the 2. Maybe it doesn't actually equal the 2, because for this graph, if I were to plug in the 2, it should be 0. I don't know if you observed, but down here, that point tells me that if when x equals 2 for this graph, our function, my y is supposed to equal 0. And that's it. Explain why if the limit does not exist, but it does, so we don't have to. Alright, B. Same idea. Let's observe x equals 2 is right. Let me highlight that. It's right here. And so from the right, it appears as though this function is at y equals 1. Oops. From the left, sorry about that, it appears that this function is at y equals -1. So what does that mean? So the limit as f of x approaches, or as, sorry, the limit of f of x as x approaches to from the right, which is the positive side, is 1. And the limit of f of x as x approaches to from the left, or the negative side, is -1. Hopefully you could see that these are not the same. They're not equal. Therefore, my limit does not exist. And so we just simply say does not exist. Does not exist. There is no limit here because they're both different from both directions. They have to be the same. We do not normally write out does not exist. We just do D and E. And a good question to have on the left side of your notes for when you're studying would be, does a hole in the graph mean that there is no limit? Okay, that's a good question. Does a hole in the graph mean there is no limit? And of course it doesn't. That was example A. Just because there's a hole does not necessarily mean there is no limit. For A, there was a limit, and it was 2. So there you go. There's a hole, but the limit does exist. It does exist. Alright, so just example 2, discuss the existence of the limit. The limit of 1 over x squared as x approaches 0. So here's our little friend 0. X equals 0 is the y-axis, right? And as hopefully you could see, there's a big old gap in this graph right there in the middle. So from the right side, this graph is getting closer to 0 on the right side, right? But then it just keeps going up and up and up and up and up and up. Not actually ever reaching 0 or sorry, and from the left, the graph is doing the exact same thing. It's just going up, 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 up. It's going or increasing infinitely. And therefore, from the right, the limit of this function as x approaches 0 from the right is positive infinity. And then the limit as x approaches 0 from the negative side of this function is also positive infinity. So then you're like, oh, okay, so the limit as x approaches 0, the overall limit of this function is positive infinity. And yeah, you would be right. But whenever our limits equal infinity, they actually do not exist. Because what is infinity? I don't know. Do you? So make note. The limit approaching plus or minus infinity does not exist. Alright, so here we have to use the graph to evaluate the value of each given quantity. So notice, notation please, A and E are not asking us for limits. They're actually asking us for what the function equals at those x values. So f of 1, that means at x equals 1, what does this graph actually equal? And it equals 2. Okay, because of this dot right here. The other two places are open, they're holes. Therefore, that's not the actual value of this function at x equals 1. Alright, f of 4, and yes, I am skipping b, c, and d just to do e, which is f of 4. So f of 4 is the same thing at 4, what does this function equal? And at 4 we have a hole. Therefore, f of 4 is undefined. Okay, because of the hole. There is no definition for what f of 4 equals. Okay, so now b. We're going to do the limit as x approaches 1, but from the left side. That's what the little negative means, right? Oops. Why won't this work? Oh, I'm using the wrong thing. My bad. Okay, so as x approaches 1 from the negative, or the left side, so this part of the graph is the part of the graph that is on the left side. Oh, no it's not. It's the part on the right. Holy crap. Here we go. The part on the left side. So for this graph on the left side, at x equals 1, the graph appears to be approaching this right here, which is about halfway. I'm going to estimate that to be 3.5. Now they want me to do for c, the limit as x approaches 1 from the right side, which is this part right here. And then for here, right, as I get closer to x equals 1, the height of the graph is about right there, which is just 1. And then d, they want me to do the overall limit. They want me to compare the left and the right and determine if there is a limit. Okay, well, if I compare the left and the right, they're not the same number. Therefore, I can safely say that the limit does not exist. Alright, so onward to f. Now they want me to do the limit as x approaches 4 from the left side. Okay, so here's 4. And from the left side, here's the left side. As I go this way, how tall is my graph? Well, it reaches the y value of 2. Or it just about reaches, except for that hole. But remember, holes are okay. The hole doesn't mean that the limit does not exist. Okay, if there's a hole, the limit might exist. Okay, so it's 2. Now we're going to do from the right side. So from the right side, it approaches the same hole, which is also y equals 2. So now for h, they want me to do the overall limit. Well, if I compare these two, they're exactly the same. So my limit is actually 2. It does exist. For example 4, I kind of want to let you try and do whatever you can on your own. So this would be a good time to pause, and then when you're done, hit play to see my answers and my explanations. I think it would be awesome if you tried this on your own. Okay, so for part A, f of negative 2, so x is negative 2. The only place is right here, that random dot. That means that for this function, x equals negative 2 is equal to that dot, which the y value for it is also negative 2. Alright, so b. Now they want me to find the limits as x approaches negative 2. So this right here. They want me to find the limits as x approaches that x value. So from the left, because the negative sign means from the left. And yes, it's not a typo. It is a minus 2 and then a minus at the end. The minus at the end is telling me from the left. So from the left, here we are. Where's it going? Oh, negative infinity. Now I'm going to do from the right, because that's what C is. So from the right, oh look at that, also negative infinity. So the overall limit, so that's part D, happens to be negative infinity, but that's the same as saying it does not exist. Alright, E. So they want me to figure out f of 0. So, alright, so there's f of 0. Now, where does the function actually equal, or, yeah, x equals 0? And there's an open hole, and then there's a closed, what do they call it? Open dot, closed dot? So the closed dot, that's what my f of 0 equals. So right here, which is 5. Okay, so f. So what does f of negative 4 equal? So f of negative 4, so right here, this closed circle, closed dot, so it is 0. Alright, G, limit, okay, so now we're doing the limit, the overall limit, as x approaches negative 4. Okay, so from the left, it's approaching 2. From the right, oh look, also approaching 2. Therefore my limit is 2. Now, does this have a consequence on this? No. Okay, no consequence. So one thing doesn't have to do with the other. Not necessarily, anyway. H. So we already found f of 0, but for h, now we're going to find the limit as x approaches 0 from the negative side. Okay, so from the left, here's the left part of the graph. You know, that's the left of 0, and it is 0. So now if I do the right, here's the right part of the graph. Should have done that another color. Let's do purple. It's the right side of the graph, and it approaches 5. And then for part J, oh, are these the same? 0 and 5? Even though my 0 looks like a 6? No, they're not the same, therefore the limit does not exist. Example 5, I love these examples. Sketch a graph of a function that satisfies the given values. As long as your sketch accounts for every single one of these requirements right here, you can almost draw just about anything. So let me draw some coordinates, or some axes. Alright, so let me brisk through here. I know there has to be an x equals negative 2 and an x equals 2, right? And I'm just seeing that from here, right? Oh boy, this highlighter's not working here. Okay, there we go. And then there's the 2 and the negative 2 again, and then there's an f of 3. So those are the x's that I know I need, so let me go ahead and set those up. Alright, so the first one, f of negative 2 equals 0. So that means that my graph actually has to equal 0 when I plug in a negative 2. I'm going to do this in blue. So I'm going to make a dot at x equals negative 2, 0. So now I know that yes, it does equal 0. Alright, the second, did that. So the second one, f of 2 equals 0. Well, okay, so this also has to equal, alright, so there you go. Alright, so the third one says the limit as x approaches negative 2 is 0. So my limit for negative 2 is 0. So that means that the left and the right are the same, and it is 0. So I'm just going to go ahead and make whatever I like here. See, from the left and from the right, it should equal negative, or 0. Right. I only made a piece because I don't know what the rest looks like yet. So the limit as x approaches 2, okay, so the limit of f of x as x approaches 2 does not exist. So how did we just learn that the limit doesn't exist when the left and the right are not the same? So I need to make that part of the graph not the same. So let's say that I make this go up here somewhere, a nice big fat dot, and then I'll make this one go down here somewhere. Okay, and then f of 3 is undefined. So at x equals 3, for it not to be defined, that means there has to be a hole. So let me go ahead and make myself a little hole at x equals 3. Okay, so that's a hole. And there I fixed the line in the middle. So there you go. Now, did yours have to look like this? Nope. It didn't have to look like this. I mean, you could have made the graph, I don't know, you could have started it here, and then like this, or just something else. It, these are open to your interpretation. Now, like, you have to have all of these things, but the graph can look however you decide it's going to look. Okay? I mean, that would have worked too. Okay, onward. Last example? Oh no, too low. True or false? If the limit as x approaches c from the left of f of x equals 2, and the limit of f of x as x approaches c from the right equals 2, then the limit that I like to call the overall limit is 2. Justify your answer. Well, is it true or is it false? Well, it's definitely true. Okay? Ladies and gentlemen, this is the definition. This is the definition of limits. And this is my justification. Example 7. If the limit of h of x as x approaches 3 is equal to negative 5, which of the following must be true? Now, not sometimes, okay, has to be true. Okay, so for the limit to exist, the left and the right hand limits have to be the same. So if you look at part 1 here, the left side left-handed limit is negative 5. Well, that makes sense because in order for the overall to be negative 5, both the left and the right have to be 5. So this one has to be true. Alright, let's look at 2. Now this is not multiple choice. Okay, there is more than one right answer sometimes. Sometimes there's not. Okay, so number 2. In order for my limit to exist and be negative 5, does my function have to equal negative 5? Now this goes back to example 1a, because let me draw you a little example. Here's my example. I just drew a graph where my limit does exist and it is negative 5. Oh, I forgot the 3. Oh, it is positive 3. Gosh darn it. Don't know why I thought it was negative 3, but anyway, I fixed it. Here is an example where the limit does exist and it is negative 5, but my function does not equal negative 5 because there's a hole. Okay, so part 2 is not necessarily true. It is false. Okay, sometimes. And just the fact that it is false sometimes means that is not a must. Okay, in part 3, h of x is continuous at x equals 3. Continuous. Hopefully you can understand the word continuous. In continuity, right, to be continuous means that you continue on and on and on without ever stopping. If I go back to that drawing that I made for part 2, this hole is kind of like stopping. It's like you're going, you're going, you're going, you're going, you're going, you're going, you stop, and then you do nothing, and then you pick up right here and you keep going. Okay? Oops. The function is not continuous. Okay? It does not continue on and on. It has a break because of the hole. Okay? The hole can be considered a break. So, does the function have to be continuous in order for my limit to exist? No, it doesn't have to be continuous. Okay, this is also false. Oh. Yeah, I was going to say something else, but it's also false sometimes. So, the only true and correct answer would have been 1. Video was a little lengthy, but it was the introduction to limits, which hopefully you have done prior. Please answer the practice problem.